think about the process that we did for the power. Well, what did we do? We brought that 5 out in front and then subtracted 1 from the exponents. That's your working forward process. Working backwards, we would want to, and we actually had these two questions in our notes, in our derivatives way back when. If you had 5x to the 4, could you work backwards? Well, most of us can just see that the answer would have been y equals x to the 5. And of course, we're going to find out now that we're going to, when we integrate or when we work backwards, we're going to always write plus c because there's a possibility that there could have been a number there. And 12x squared, working backwards, you'd be like, all right, I know this has got to be a 3. You would probably do a mix right now of working backwards and working forwards. So you'd be like, I see that there's a 2 there. I knew that there have to be an x cubed. That 3 would have to come out in front. So what number would have had to been in front originally when that 3 comes out to get me the 12? It would have had to have been a 4. But what we're going to do is we're going to go through that process and say, well, if this is step 1 and step 2 moving in this direction, if I wanted to work backwards, first I'm going to add 1 to the exponent, because that was the second thing I did when I did the derivative. And then the first thing I did with the derivative was multiply by the exponent. So to undo that, the opposite would be dividing by the exponent. So if we go back to this question, now as a working back process, if I added 1 to the exponent first, I would have that, leaving the 12 out in front, and then saying I'd have to divide by that exponent, gives me the 4x cubed in the same way. And then, of course, step 3, which is new, we're going to add a constant c because there could have been any number at the end. So here's the general formula. If you're integrating any power law, you're going to add 1 to the exponent and then divide by that exponent to compensate for the fact that if you now did the derivative, that exponent would come out in front. That allows us to have any number or constant in front, which is in part B. You have any number in front, you just can ignore that number, just add 1 to the exponent and divide, and not have to think about the mental math. Right? Because here, initially, when you were working backwards, you were doing mental math thinking. You were thinking, I had to have a cubed here. And then imagining what number would have had to have been in front to begin with to get me the 12. And then 4 times 3 is 12. Which is fine if the numbers are nice. But if I would do this same question with dy dx equals, let's make some not nice numbers, 3/7 x to the 5/3. That's the derivative. What's the original function? Well, adding 1 to the exponent would be not too bad, right? Adding 1 to this exponent would get me 8/3. And what would you have to have out in front? So when you bring that 8/3 out in front, you get 3/7. And I see that nobody was like on the tip of my tongue, like 1 + 1. You're like, 2, I know that one. It's not an easy number to put there. So now what we're going to do is we're going to say, I'm going to just leave that 3/7 there. I'm going to add 1 to the exponent. And just like in derivatives, you got really good at subtracting by 1. In integrals, you'll get really good at adding 1. And divide by the 8/3, which is the exponent. Because if that 8/3 came out in front, it would have to cancel out with this 8/3 on the bottom. And then, of course, you can use your fraction rules, like dividing by a fraction is the same as multiplying by the reciprocal. Wow, that's a bad 7. 3/7 multiplied by the reciprocal 8/3. Did I not flip it right? No, I didn't flip it at all. Sorry. Flipping it would give me 3/8, which would be, oh, obvious that the number in front would have been 9/56. Not as easy to see. And then, of course, we'll add a plus c at the end. Some of you on your integration test, the very first thing you're going to do at the top is write plus c. So you're like, I can't forget that plus c at the end of my integration. So this is working backwards with, my computer has hiccups today. So what we're going to do is we're going to add 1 to the exponent. And the indefinite integral, we can write with this indefinite integral sign. The dx part says that you're integrating with respect to the variable of x. Add 1 to the exponent and divide. And then plus c. And right here, I'm still putting the fact that c can be any real number. On a test, if you just write plus c, I'll know that you're assuming it can be any real number. So try these next couple on your own. And they'll have some things like the square roots. You're going to have to change that to a rational exponent. I'll put the answers up in a bit. Change the square root of x to x to the half, then you can add 1 to the exponent and divide. And personally, I would leave it like this with the fraction on the bottom. I mean, you can simplify if you want. On your exam, if you leave things unsimplified and they're right, you get full marks. If you simplify them and make a mistake, you lose a half a mark or a mark. So, where do you have to simplify? Multiple choice questions, right? It's not like, oh good, I can forget how to do all of that math. No. That still has to be there, especially for multiple choice questions. But on long answer questions, you could leave it like that. But chances are these happen to be more likely multiple choice questions anyways. So again, take that 7th root, make it x to the 3/7, add 1 to the exponent and divide. And of course you could leave it like that, perfectly fine, or you can multiply by the reciprocal. So what we're going to do in integration is figure out what we can work backwards with, what things are possible, what things are too difficult, right? Because like quotient rule is very difficult to work backwards from, especially when most of the time things have been simplified. So we will have certain things that we'd be like, I can't work backwards easily. You have a derivative rule for adding and subtracting, which says you can take the derivative of each of them separately. So we also have an integration rule that if you are integrating something that's adding and subtracting, you can integrate them separately. So if you have the integral of x to the 5 minus 3x plus 2, you can integrate each of those on their own. See if you can work backwards. Add 1 to the exponent and divide. What are you going to do with the 2? Quick check. How do you do to get x to the 6 over 6? And I'm going to put a purple box around this step right here. You don't even have to write it if you don't want to. This is not necessary to write. I would expect you to go directly from the question right to the answer, integrating each one separately. But it's just showing the rule that we are allowed to integrate separately when we're adding and subtracting. You are not allowed to integrate separately if you're multiplying or dividing. So these rules are like, it seems intuitive, but we have to be careful because every little thing, like this next one, is multiplying. You cannot integrate the x plus 7 and then integrate the x minus 3 and multiply your answers together. You can only separate things if you're adding or subtracting. So what we need to do is we need to multiply this out. And we have to get it into a form that's easy to integrate. And now we can just add 1 to the exponent and divide all the way through. I simplified that second term, but most of you will probably start writing 4x squared divided by 2. Try the next one. What can you do with that one to get it into a form? Right now, the only thing we're able to integrate is your power rule. How do you figure out how to work with that second one? And then the one at the bottom is easier. And while you're working on those two, this is very similar to that paper that we did. I guess it was last week on Wednesday. It has a list of every function that we've done. And their antiderivatives. Okay, so if you factor the original function, it simplifies to x minus 4. Then the integral would be x squared over 2 minus 4x plus c. Technically with a restriction that x still can't equal 2, because that's a non-permissible value in the original. And the last one here. First, I would change the cube root of u to u to the 1/3. Add 1 to the exponent and divide. And I would probably leave my answer like this. But I could take that dividing by 4/3 as multiplying by the reciprocal. And that would be simplified. Now I just handed out that purple sheet of a list of functions and all their antiderivatives, which is jumping ahead. So we've got a couple more examples. I flipped my page too soon. Now in integrals, just like in derivatives, if you have a constant k, it doesn't affect the derivative. It just is out in front and stays out in front. And well, of course, it still affects the answer, but it doesn't affect your rules. The same thing with integration. So if we're manipulating integrals with integrals, we can pull that number out in front. And so if I want to do that, it can sometimes make seeing the integral easier. So for example, I have 4x cubed here. If I wanted to find the derivative, I would first change it to 4x to the minus 3. And the minus 3 still comes out in front. We still subtract 1 from the exponent. So that 4, when that minus 3 comes out in front, becomes a minus 12. And you could write it this way as well. Now, if we are integrating, we could pull that 4 out in front. We wouldn't have to. We could leave it inside. But now we add 1 to the exponent and divide. That number that was out in front is still out in front. And you could simplify this if you wanted to. So if we wanted to integrate something like this, step 1, I would take that fifth root and change it to something that I can work with. And I can pull that 30 out in front if I want to, or I could keep it inside. Basically, that constant's just going to stay there. So I would rewrite my 30, add 1 to my exponent, divide by my exponent. If you added a plus c at this stage, this would be perfectly fine to leave your answer like this. But we could multiply by the reciprocal and reduce it if we wanted to. So if it was multiple choice, it might have been reduced all the way. So now if the integral is working backwards of the derivative, it's kind of like the idea of an inverse, but not quite. It's a little bit different. So if you were doing the integral of a derivative, does it make sense that you would just get the original function that you started? So this question says, find the integral of the derivative of 5x squared. So if we were working step by step, first I would do the derivative of 5x squared and say, that's 10x. So my question becomes the integral of 10x dx. And then finding the integral says I should add 1 to the exponent and divide. And what do you notice? I get 5x squared again. But I still have the plus c. Now, if we were going the other way, if we wanted to find the derivative of an integral, the integral would be add 1 to the exponent and divide. And then the derivative of this would be the negative 2 would come out in front, subtract 1 from the exponent. And then we still have the derivative of c. So if you do the derivative second, there's going to be no plus c. If you do the integral second, there will always be a plus c. But the basic idea is the derivative of an integral or the integral of a derivative. Those are taking one step forward, taking one step back. You're back to where you began. They're going to cancel each other out. So the shorter way in the first one is saying, okay, the integral and the derivative are going to cancel out. I'll just get 5x squared. But since I do the integral last, I need the plus c in that one. Derivative of the integral would mean they're going to cancel out. And since I'm doing the derivative last, there's going to be no plus c because the derivative takes any constant, makes it 0, and it would go away. And here's the purple page that I passed out to you. This is working backwards of everything. And there's a first page, and there's a second page. And you can actually ignore the second page because cos inverse, cotangent inverse, and cosecant inverse are no longer necessary when working backwards, because you can just work the negative into the other ones. You can think of the negative, because you see that your cos inverse, cotangent inverse, and cosecant inverse are just negatives of sine inverse, tan inverse, and secant inverse. So you can just work the negative as a constant inside. So the front page is really important. You can use the back page. It might be the back page sometime would come up on a multiple choice question. But you can get away with just the first page of these derivatives. If you just have a number, straightforward, right? Derivative of 2x is 2. So if you just had a 2, working backwards would be a 2x. Here we have our product, our power rule that we were working with before. This one is sometimes tricky to see, right? Because the derivative of a natural log is 1 over x. But noticing a 1 over x and thinking of a natural log is even harder. So that one I'd put a star beside, okay? And then a little bit of a noticing thing is that when we integrate with the natural log, we add absolute values because you're not allowed to take the logarithm of a negative number. But 1 over x is allowed to have negative numbers, right? So in integrating, this domain could be everything. Then how do we make this domain everything as a result? We need those absolute values. Technically, when you integrated the natural log, when you took the derivative of the natural log of x had already restricted the domain from 0 to infinity. And so the derivative of the natural log of x was only half of the 1 over x graph, just the positive half. E to the x will continue to cause problems because it doesn't change, which is really nice and sometimes, but sometimes it makes our head hurt. If the derivative of a to the x was a to the x times the natural log of a working backwards, you have to undo that multiplying. The opposite of multiplying is dividing. So we're seeing this common theme of a lot of derivatives had a multiplication after the fact. So a lot of integrals will have a dividing. Sine and cos. Oh my goodness. One of them has a negative, one of them doesn't. And now it flip-flops when you're working backwards. So for me personally, I always look at the derivative of sine from a graphical approach. So if I have my sine graph here, and I think of derivatives as slopes of tangents, because if you think about what does a derivative actually do, it figures out the slope of a tangent. For me, this helps me remember that the derivative of sine is positive cos. And that's the only one I really remember well. I mean, I probably remember them all pretty well by now. But that means the derivative of cos is negative sine. And then when working backwards, if I know the derivative of sine is cos, then working backwards, the integral of cos, that will stay positive with sine. But the integral of sine is now negative cos. So having those positive and negatives, really easy to mix up. Have some way that you're going to remember that. So we can integrate secant squared to get tan x. It is not easy to integrate secant all by itself. We can integrate secant tan x as secant x, cosecant cotangent as negative cosecant x. So now those negatives are getting switched to the other ones. And then here are your three inverse functions that you'll need to remember. If you had a negative out in front here, you could just call it negative sine inverse of x. If you have a negative out in front here, you could just call it negative tan inverse of x. And if you had a negative out in front of this one, it could just be negative secant inverse of x, which some textbooks don't even mention these last three as a result. So take your purple page and try the next three questions. Try to do them without looking. You can actually do them. You can do them on there, but you can do them in your notes too. You have an old version, the new version I forgot. All right, I'll put up the answers for the first one. Again, you wouldn't need to simplify to the second step, but if you wanted to, you could. I like just doing one step. I would keep that -1 on the bottom. Unless I needed to do some other math later, but if it just asked me to find the antiderivative, just do it in one step. One thing that's going to take some time is remembering those absolute value bars on the natural log. And after curve sketching, you sort of have had a break from some of your derivatives for a bit, because we don't curve sketch a lot of tan inverse and cosecant inverse. And there wasn't a lot of natural log powers of different values, trig functions. So it's a good opportunity to take some time, test your derivatives, and test your antiderivatives. Okay, so how many are on the front page here? 3, 6, 9, 12, 15. 18 if you count the back. There's 18 of them. 12 of them have to do with trig. So that only leaves 6 other ones. test yourself if you can say them all and do their antiderivative, derivative and antiderivative. Try working both ways without looking at your paper. Can you say all 18 of them? And if you break them up, trigonometry, okay, trigonometry has 12 of them. Then after that, e to the x and 5 to the x, natural log of x. Oh, I guess we didn't put just the regular log of x. That would be a good one to think about as well. Make it 19. And here's the last one. I simplified it, but definitely could have left x to the 3 halves over 3 halves. Perfectly fine.